Today's topic is rotary motion. Rotary motion is different from circular motion that we just studied. An object that's moving in a circle is moving around a point that's external to it, not inside its own self. So like an example, this would be the Earth rotating around the Sun. Here's the Sun, here's the Earth. The Earth revolves around the Sun one time per year. On the other hand, rotary motion, an object is spinning around its own center. That would be rotary motion. So you can think about the Earth also doing this. There's the Earth. The Earth spins around its own axis one time per year. That's an example of rotary motion. It rotates around its axis. Circular motion is caused by centripetal force. We learned a bit ago that centripetal force can be quantified by m times v squared over r. That's what causes circular motion. Rotary motion, on the other hand, is caused by a torque. So if you have an object and you want it to get spinning around its own center, you have to apply a torque to it to make that happen. Just like we can quantify the motion of objects that are in translation, that are moving linearly, we can also quantify the motion of objects that are exhibiting rotary motion. We used distance to describe linear displacement. Well, we're going to use angle or rotary displacement, and this is usually specified with the Greek letter theta. Sometimes we can measure this in degrees. That's typically how you do it in geometry classes and things like that, but it's much more useful for us to use radians in physics to describe displacement in most cases. When you're measuring an angle in radians, what you're really measuring is you're finding the ratio of how far the object moves along the arc on the outside of the motion to the radius of that motion. That's what we're really measuring. And so the angle theta measured in radians is, if this is delta d here, it's delta d divided by r. That's how we define radians. Radians are just kind of a made-up unit, and they're kind of goofy when you're used to working with degrees, but they're really handy because they end up being unitless. Distance around the arc length there, that would be measured in meters or inches or something like that, and radius could be measured in the same thing. And so they cancel out, and then radians is a unitless number. Well, here's an example problem that we can solve. A bike wheel with a 700 millimeter diameter rolls across the floor 1750 millimeters. What's its angular displacement? Well, by definition here, angular displacement in radians is delta d divided by r. So we know that it's going 1750 millimeters. That's delta d. And the radius of this is going to be half of the diameter. It's 750 millimeters in diameter, so that would give us a radius of 350 millimeters. And once again, the units cancel out just like we'd expect. And the answer that you get is 5. This has gone through 5 radians. We can develop a way of converting back and forth between degrees and radians if we think about the circumference of a circle. If we went through the entire rotation, one entire rotation around a circle, we would have covered a distance of, well, the circumference, which would be 2 times pi times r. That would be essentially delta d for rotating one complete revolution. And the radius, of course, is r. And so theta in radians is 2 times pi times r, that's delta d, divided by r. Well, r drops out of here, and our angle, when we go one complete revolution, turns out to be 2 pi radians. Some of you already knew that from a trigonometry class or something. Well, that means that we now have a unit, a conversion unit. 2 pi radians, remember radians are unitless, so I'm not putting a unit there, is equal to 360 degrees. Let's use that fact to solve this example problem. The question here is, what is 60 degrees expressed in radians? Well, let's start out with 60 degrees, and then we'll just use a dimensional analysis technique here. 360 of those degrees is 2 pi in radians. And so we can solve this problem. It turns out to be 1.05. Remember, no unit, because radians are unitless. You might notice that 2 pi and 360 could be reduced a bit and give us another factor, and that would be pi over 180 degrees. So you could solve with that conversion factor as well. Here's another problem. A pulley with a radius of 5 centimeters. So here's our pulley. got a radius of 5 centimeters, rotates through an angle of 270 degrees. So theta, it's going to rotate 270 degrees, but theta is in radians converted this way. 180 degrees goes down here, pi can go up here, and we find when we do the arithmetic that we have an angular displacement of 4.71 in radians. And what we wanted to know here was what length of rope has been moved by the pulley. The length of rope that's been moved by the pulley is the length that just gets wrapped up. In other words, it's the delta D in our radian definition. So since theta is delta D over R, it would follow that delta D, which is going to be the length of the rope wrapped up here, would be theta times R. So I take my 4.71 radians, the unitless number, and I'm multiplying it by my radius, and it says my radius is 5 centimeters, and that leaves me with 24 centimeters that the rope has been wrapped up. Well, here's another problem with the same pulley, radius of 5 centimeters again. It rotates through an angle of 270 degrees, so that's the same as before. But now this radius doesn't have a rope wrapping up around it, it has a belt. And that belt goes around another pulley. That pulley has an 8 centimeter radius. So here I've got 5, here I've got 8 in centimeters. And what these two pulleys have in common is this. They're going to pull the same amount of belt around them during this period of time. And that would be 24. Well, if theta is delta D over R, and we know that delta D is constant, well, we could say that R times theta for one pulley would have to be R times theta for the other pulley. And so we can make ourselves a little toolbox item here. We can use this to solve for this problem here. Radius 1 is 5 centimeters. Theta 1 was 4.71 radians. Radius 2 is 8 centimeters. And so theta 2 can be obtained in this way. Centimeters drop out, and I will get the unitless radian measure, and this ends up being 3 radians. We have lots of rotary motion situations that have pulleys and gears. And we've just seen in the last problem what is the relationship between R and theta exactly, and it's this. R1 times theta 1 is R2 times theta 2. So this is a useful relationship between these two quantities. The same rule would apply to gears. The only thing that's different about gears is instead of having a belt that moves both pulleys in the same direction, when you have gears, they interact by teeth and they move in opposite directions. So the direction of rotation is reversed, but it's still true that R1 theta 1 for the first gear is equal to R2 theta 2 for the second gear. And diameter is just 2 times R. So if you had 2 times R times theta, R1 and theta 1, and you set those equal to 2 times R2 times theta 2, that would just be multiplying both sides of an equation that we already believe by the same number, by 2. Well, so that means that diameter 1 times theta 1 is diameter 2 times theta 2. So we can use diameter and radius interchangeably depending on what's easier. Another thing that we can use, this is handy for gears, is that the gears, if they're to mesh together, these gears have got to be the same size. So teeth, gear teeth, is actually a way of measuring diameter or circumference. And since diameter or circumference are proportional to each other, then we can substitute teeth when we're talking about gears for diameter or radius. And so here's another equation that we can use. Teeth 1 theta 1 is teeth 2 theta 2. Don't get confused between teeth and time. This relationship is useful for gears. Just like we can describe linear displacement and then move on to velocity as the change in that displacement with respect to time, we can do the same thing for angular motion or rotary motion. So theta, if a change in theta happens in a certain amount of time, that's what we would call angular velocity. Angular velocity is described by this Greek letter omega. So there's a definition for us that's really an analog of the translational motion. V is delta d over delta t. Omega is delta theta over delta t. It's the rate of change of angular displacement. You can use any units of angle or any unit of time to get an angular velocity unit, but there are two that are really common. One we use all the time in the U.S. and probably all over the place in describing rotary motion, and that's RPMs, which stands for revolutions per minute. So that's very common. But the one that we probably are going to end up using a lot more is just radians per second. But radians per second is just per seconds because radians are unitless. Well, here's an example problem. Question is, if a crank is turned through 720 degrees in 5 seconds, what's the angular velocity? Well, angular velocity, omega, is defined as the change in angle over the change in time. So the change in angle is 720 degrees, and the change in time is 5 seconds. We're supposed to specify this in two different units. The first one is radians per second. So let's do a little conversion here. Let's just tack on to our angular velocity a conversion factor, and that is 180 degrees is pi radians. When we do this calculation, what we find out is that we've got 2.51 per seconds, or 2.51 radians per second, you might say. We also want this in RPM, so let's do the same thing here. Remember, it's delta theta over delta t, starting out with our angle of 720 degrees divided by 5 seconds. That's our angular velocity. But let's convert. First of all, we're going to convert degrees to revolutions. Every revolution, 1 rev, is going to rotate you through 360 degrees. And then that will get us degrees gone. Now we'll have revolutions per second, but we want revolutions per minute. So we'll use the conversion factor that 60 seconds is the same thing as 1 minute and get ourselves some RPMs here. And in revolutions per minute, it's going to be 24. Another example problem, an engine is turning at 4,000 RPMs. What's its angular velocity in radians per second? So this is just really a dimensional analysis problem. 4,000 RPMs means 4,000 revs per minute. We want seconds in the denominator, so we can say 1 minute over 60 seconds and cancel off the minutes. But we also know that a revolution is going to turn us through 2 pi radians. We discovered that a few slides ago. So this gives us a setup that will end up with a velocity, angular velocity, in just radians per second, or per seconds. Do the arithmetic and you find out that it's going 419 radians per second.